Thanks, John. Welcome, ISR signal processing fans. So I'm going to talk at a slightly higher level of abstraction and cover a bit more of a heterogeneous approach to selecting the best processing for what are very swap-constrained sensor payloads, right? So there's quite a bit of choice in terms of processing elements. So before we actually get into some of the choice there, just a quick review of, in terms of ISR, if you look at green, SIGINT's a big subsection, of course, radar in blue, large subsection, and imaging, so EOIR there in purple. I've also included electronic warfare in red with the three different subsections there. And I like to think of ISR, if you will, as being strategic and EW as being a bit tactical. A lot of these systems historically have been stovepipe, but what we're certainly seeing is systems that have multi-mission payload applications. So, for instance, there are a lot of applications that we're starting to see that just require not just a ton of FPGA slices, for instance, gigaflops, even teraflops. A lot of that quite often can be associated with the fact that we're not just trying to do an advanced SAR radar. You may be combining SAR imagery with, you see WAS there, wide area airborne surveillance data, so that this is gigapixel focal plane array data from electro-optic, infrared, multiple cameras perhaps, and even combining that with an overlay, say from an ELINT system of RF emitters in the effective order of battle. So if you think about that, even from just one aerial platform, that's a lot of compute power to correlate both in space and in time. And what if you're doing that from multiple platforms that are sharing data? It's a tremendous amount of compute power there. There's also other interesting challenges, especially on the RF side, for instance. You see requirements for some programs where they want to have a jamming capability, but they also want to be collecting data as a common system. So it's like yelling in your own ear. There's a lot of very sophisticated challenges that require some innovative compute. And so we have a rather complex chart here, and you see a picture of the periodic table on the left. And so if we start at the atomic level, there's more choice than ever. So there's the classic power architecture where the latest in vector processing, AltiVec-enabled processors, we still see, for instance, processors from Freescale, which Curtiss-Wright, there's a lot of systems which we still combine with Intel because they tend to be better in terms of safety critical for avionics. Intel in particular, there's four large categories, many of which Curtiss-Wright play in here. We do a lot with Core i7. Atom tends to be very, very power efficient. There's something called Xeon D, which is really very, very exciting for the defense ISR community because it gives us the x86 cores, pool of cores, great for multi-mission computing and so on, but in a much more accessible package than the larger Xeons. Discrete GPUs, I think, are coming back in terms of a second wave. There are just the teraflops you get, the actual performance per unit power, so teraflops per watt, it's undeniable. FPGAs, these are the I/O chameleons, critical for being towards the front of the sensor, like Roger was talking about. And then finally, there's a whole category of hybrid technologies. The Core i7 itself in your laptop has both x86 cores and ever-expanding GPU, which you not only can render graphics, you can actually accelerate math. And there's some great software paradigms coming out, such as OpenCL, that enable that. Actually, one point about OpenCL in particular, this is something that's starting to span across all of these processing technologies you see here. So as just being relegated to VHDL and Verilog on FPGAs, CC++ and x86, and CUDA on, say, NVIDIA GPUs, OpenCL is something that can bridge the gap there. Very exciting. There's also ARM cores appearing in everything, in Xilinx parts, in GPUs, in TI parts. So there's a lot of choice. So today, if we look at an ISR and EW sensor processing chain, what tends to, and this has been the case, I think, for a few years, but I do think this will continue to evolve. You see this heterogeneous combination of typically FPGAs that are up near the front. You may have wideband analog ADCs that, in fact, Curtiss-Wright has 12.5 and even 25 gigasample per second ADCs, just a massive influx of data. FPGAs, of course, great for decimating that down with GDCs or binning with FFTs and so on. Intel x86 cores, lots of them, especially in multi-mode radar, multi-mission computing, where you have to change what you're doing on the fly, can be a very valuable asset. Now you see the GPUs are kind of hanging off that, and those may be discrete GPUs where a heavy-duty cycle portion of your signal processing algorithm, you may relegate that to the GPU. Now that whole CPU-GPU complex can be a single Intel device where those GPUs are actually the embedded GPUs in your Core i7. We see that trend a lot. Continuing on, single-board computers are often at the conductor's helm, but for I/O, there's a lot of I/O besides just the front-end sensor ingest. There can be storage for radar environmental simulators, for instance, and just general-purpose I/O. And then finally, the concept of a switch. And this is not just for switching the data plane to get data across the system. There's also the control plane, the management plane, which is kind of a nervous system. There's been some evolution there as well. We've seen serial rapid I/O in recent years, but that has evolved to 40 gig E and InfiniBand. But I think we'll see that evolve beyond this, of course. So if we just kind of break down that sensor chain, first of all, FPGAs quite often at the front, right behind lots of wideband ADCs. So there's a lot of systems that Curtiss-Wright will construct that this is just a single board architecture, but it's often many boards if there's lots of ADC channels. So this is where, for instance, you're conducting beamforming, or say, for instance, in a SIGINT EW app, like a time difference of arrival, this is where if you want a very, very fine, for instance, circular error probable, if you're trying to stare at something that's 20 kilometers out and you want to know within a very reasonable amount of certainty where that thing is, you want those ADC converters synchronized down to the sample clock, in fact, down to the rising edge of the sample clock. And we're talking the inverse of like a gigasample per second ADCs and being in picoseconds, and rising edge, it's femtoseconds. I mean, these are very small units of time, so it's a lot that goes into keeping something coherent, a number of channels coherent. So for instance, the ChampFX4 is just one example of a popular Vertex 7 architecture that we have, where we use what are called FMCs, FPGA mezzanine cards. So this is a VITA standard. There's lots of FMCs that we support, including homegrown ones in Curtiss-Wright, but we also leverage from third-party partners such as Delphi and Ford DSP, et cetera. This particular architecture shows you a couple of Vertex 7s right behind those FMCs to take in the ingest and Sometimes you have 12-bit ADCs that are sampling gigahertz of intermediate frequency. Sometimes it's 16-bit, more channels, more popular in common systems where you need the kind of dynamic resolution required to do a DMOD, and then you may combine that and move along into the system. Now, another example, instead of RF input, imaging, quite often we'll have a focal plane array. FPGAs are also popular to ingest that data, strip out protocol, for instance, move it along to GPUs, discrete GPUs sometimes directly, or to embedded GPUs within the Intel devices. Now, one example of a Core i7 DSP card that Curtiss-Wright has, and you see a picture off in the upper right, that's actually the Core i7, this is Haswell. What's really neat about the GPU in here, you not only have the x86 cores all cache coherent, you have that integrated GPU right on the die. So as opposed to discrete GPUs where you typically have to go off via PCI Express, you can actually realize very low latency transfers between those x86 cores and the GPU. So even electronic warfare apps, which often have associated latencies that are measured in nanoseconds, you can actually start to realize the hundreds of gigaflops or even teraflops that GPUs offer. So the Champ AV9 is an example where we not only have PCI Express, which if you do need other assets such as large discrete GPUs, the blue lines represent, especially going to the backplane, 32 lanes of Gen 3 PCI Express. That's a lot of data. The green lines represent the data plane. This is what attaches to the fabric, the OpenVPX fabric and the data plane. So that's either 40 gigabit Ethernet or InfiniBand. What's new with this module is that you actually can render displays, not just use the GPUs for accelerating math with OpenCL, but we have customers, for instance, that are using a module like this to actually render displays in ISR systems to operators, and those red lines represent 6 individual displays. So there's a lot going on here. This is a very complex card, 32-layer. It's really a feat of engineering, and it's fully ruggedized so that whether it's air-cooled or fully conduction-cooled, this module can go in some very rugged ISR payloads. Okay, and coming down the home stretch here, what we're up to, the latest thing we're up to, from HPC to HPEC, what we're saying there is high-performance computing. We're talking about, there are defense primes, for instance, with, you see an IBM blade center on the top and a typical compute rack on the bottom. There are benign systems, say, on surface naval vessels and ground radars where there's a lot of, the primes have a lot of intellectual property tied up in radar algorithms and so on. And they need to get that into a UAV or something that's ground mobile. It's not just about porting software. It's more than that. You need those compute elements to go with you. You need as much memory as possible to go with you because they're used to a lot of memory, and as much of that I/O. And that's what we're effectively doing. I'd mentioned this new device, Xeon D, which Intel's, one of its commercial groups, has announced. And you'll see other announcements in the future. Xeon D, effectively, the one way to think of it is the Core i7 that's in your laptop, the GPU is pretty big that's in there. So if you actually take that out, it affords you a lot of room in the die to put more x86 cores. So this is basically a BGA extended temp part, or assume it eventually will be from Intel. And what Curtiss-Wright announced last week is, by the way, a 3U and 6U board pairs. So I've been talking 6U. We have a full portfolio of 3U. So the 3U analogy is completely there. So we see big trending with both. So for Xeon D, we have something called the Champ XD1. This is just great in terms of multi-mission ISR compute. Lots of x86 cores there, starting with 8, and it'll go beyond. I/O, so you can put an FPGA XMC there with an ADC. There's the big thing that's changing here is not only is there lots of Gen 3 PCI, but there's 10 gigabit Ethernet coming alive that's native to the Xeon D. Very cool. The Champ XD2 is kind of an evolution of the Champ AB9. It leverages all of that good PCI Express expansion plane and also 40 gigabit Ethernet or InfiniBand. But instead of having the capability to render displays, it's just a lot more x86 cores. So it's more of a homogeneous kind of high-performance compute system. So needless to say, we'll be attacking other processing elements in other form factors, and obviously there's a lot that goes into building the subsystem in terms of getting the backplane right to be able to handle the high rate of transfer here of data and also the enclosures. And with that, John, I'm going to hand it back to you. Thank you.